So in this lecture, we're going to do a little bit of an application here. What we're going to do is we've already introduced our vector spaces a long time ago. We talked about norms a couple lectures ago. We're now going to show how vector spaces with their norms get a topology. That topology allows us to discuss convergence, and that convergence allows us to discuss completeness. And the way we're going to demonstrate all this is we're just going to run a proof, and kind of throughout the proof, hopefully all of this path will become evident. But our proof is going to be the following proof. We're going to prove that all finite-dimensional normed vector spaces are complete. We're doing this for a couple reasons. One is I kind of want to show an example of how the finite dimensionality of things is very important to understand these basic ideas. Completeness is not too difficult to grasp. The idea is that we have a sequence of vectors, phi n, that converge to a vector, say psi, and psi is an element of the vector space, right? So all of our Cauchy sequences should converge to a vector space. But the idea of a Cauchy sequence, let's get that right. The idea of a Cauchy sequence only means anything if we have a norm, right? Because the Cauchy sequence is phi n plus 1 minus phi n, right? That has to be decreasing, right? Getting smaller and smaller and smaller. In fact, it has to always get arbitrarily small. But in order to understand a Cauchy sequence, you have to have a norm. Imagine if you didn't have a norm, right? Then you would end up with psi n plus 1 minus psi n equals some other vector, right? And there's no way of understanding how close these guys are because that's just another vector in the space. You can even imagine a situation where you have, say you have 1/1000th times a basis vector E1, and from that you subtract 1, I got to get an even smaller number, say 1, let's see. Let's just say it was 1 over n plus 1, so 1/1001th, right? So you have a E1, right? So this is going to basically be a very small number times E1. Well, we know something about how real numbers operate, right? Whoops, we have topologies on real numbers. So we know how this difference between 1/1000th and 1/1001th would be, and we know that this number delta is getting tiny. But with this guy here outside, that still doesn't really tell us the distance between these two vectors because it's not a real number. It's just another vector. No matter how small this coefficient is, we want to say that this is close to the zero vector, right? But we really can't because just because this coefficient is small, there's no way to interpret that as being close to the zero vector inside the vector space. The thing you need, of course, is a topology on the vector space that will allow you to get some kind of notion of convergence. The topology has to be not just any topology, it has to be one good enough to give you a sense of convergence. And we talked about that before, and this norm is going to be the thing to do it. So we're going to demonstrate this idea. So basically we need finite dimensionality. The need for that will show up in the proof. Normed vector space, that's the norm is based on this idea. A Cauchy sequence doesn't make sense without a norm. And then we'll show that it's complete, meaning that the limit of all these Cauchy sequences in finite dimensional vector spaces are, in fact, in the vector space. So let's begin. All right, so let's have a look at how we're going to attack this problem. V is going to be the vector space under consideration, and S is a set of basis vectors. It's a finite set because we've assumed that V is finite dimensional. So we have a finite set of basis vectors. An arbitrary vector psi will be decomposed in the basis using the coefficients alpha, and alpha we'll treat as real numbers. Alpha is going to be real numbers. Then, in order to make this proof work, we have to prove an intermediate lemma. And that's not uncommon in analysis. It's not uncommon in all mathematical proofs, right? You need to prove what you ultimately want to show, which is that V is complete, a finite dimensional normed vector space V is complete. we need to show this lemma. Now the lemma we want to show is this very interesting thing right here that was concocted by, I'm sure, some 19th century mathematician. But what we want to show is that for any vector in the space psi that has this expansion, that has an expansion, and any vector, of course, does. We've already proven, right, that every vector finite dimensional vector space has a Hamel basis, which is exactly what this is. It's a finite psi is expanded in a finite number of basis vectors, which makes perfect sense for a finite dimensional vector space. It's pretty trivial. We take the expansion coefficients and add up their absolute values, and that sum of those absolute values, and then we divide by the norm of psi, whatever the norm is. We do not have to identify the type of norm. It just has to be a norm that satisfies the rules of being a norm, right? And that ratio, no matter what vector you choose, that ratio will always be less than some identifiable number m. And likewise, we could write it this way. We could write it this way, where that ratio is greater than that sum of the moduli multiplied. The norm is greater than the norm will always be greater than the sum of its moduli multiplied by some identifiable number h, and that's a fixed number. This doesn't change. This is identifiable for every vector in the vector space. And so we want to prove this, and what's the relevance of this is that this is going to ultimately help us squeeze the values of alpha, or squeeze our series into something that converges, and we'll see how that works in a moment. You can almost tell because I have an epsilon here. I'm defining m, which is a very relatively large number. You can imagine. I guess you can imagine a circumstance where a vector space assigns a large norm to, say, a small sum, and m is wait a minute. Whatever m is, epsilon is just defined as its reciprocal, is what I'm trying to get at. But the key, I guess, I should leave with is we're going to operate using this statement here, which is equivalent to this, and I'm using the letter h now to represent some small number, right, that when multiplied by this sum will force this sum to be less than the norm of psi. So I guess what I've done is I've taken psi and I've moved it to this side of the equation, and I'm multiplying by, and then I divide this by some large number m, or equivalently multiply by a small number epsilon, and ultimately I have this expression where h is some small number. So this is kind of an interesting way of looking at it. You can say that the norm of a vector, of any vector, is always greater than the sum of the absolute values of its components multiplied by some number h, which is identifiable in the space. But this h would be true for every vector in the space. You only pick one h for every vector in the space. It's obviously true vector by vector. You can always find some tiny real number that's going to shrink this down to be below your norm. But the fact that you can pick one for the entire space is what's important. So this is kind of where we start, and we're trying to show that that is true. And what we're going to start by doing is assuming the opposite. We're going to assume that this condition is not met. So our assumption is going to be, this is our assumption right here, I put it in red. We're going to assume that there exists a vector in the vector space such that the norm of that vector will be less than h multiplied by the sum of the vector's components, the absolute values of the vector's components, for all h greater than 0. For all h greater than 0. That's the same thing as saying this h doesn't exist, where this is greater than this for some h. So no matter what h I pick, this norm will always be less than this this product. So h can be very, 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 very tiny, yet I will still find a norm that is smaller than h times the sum of its components. So that's the assumption, which is the opposite of what the lemma is trying to prove. So in particular, if I pick h to be 1, 1/2, 1/3, or 1 over any integer in this sequence, I should always be able to find a vector psi sub m, where m is, say, the denominator of my choice of h. I should always be able to find a psi sub m which is expandable in the basis, and its expansion coefficients would be ai, phi I, just as before. But now, because I've named this thing m, I've got to put a little m on these components just to show that those alphas are associated with this particular vector. And it has to also be true that the norm of psi m is less than this expression, right? It's less than the sum of its moduli, which are these, the sum of of the absolute values of its components, which are given here, and divided by m. And divided by m is effectively multiplying by h, which is this increasing sequence. So for every value of h along this increasing sequence or decreasing sequence of real numbers that approach 0, I should always be able to find a vector in the space where this is true. And if that's the case, then this would be false. Now, because we have assumed that this condition is true, that this thing always exists, we assume the existence of phi m for every value of m. And therefore, we can create a sequence of vectors in the vector space, and that sequence is phi m, and it's indexed by m. And that's a sequence of all the vectors in the vector space that satisfy this condition given this sequence of these small values h. So we've now created a sequence in the vector space, and that sequence exists by assumption. So from this sequence, we're now going to create a second sequence. And that second sequence will be called gamma m. And the sequence gamma m, so we started with psi m, the sequence gamma m that we're going to create from psi m is that each vector gamma m is going to be psi m multiplied by the reciprocal of the sum of the absolute value of the components of psi m. And since psi m itself, so it's basically gamma m is just a factor times psi m, and that factor is tuned to each psi m by the psi m's components. Now we know psi m exists by assumption for every value of m, and therefore we know gamma m exists for every value of m. Now the beauty of this choice is that it implies that the norm of gamma m is less than 1 over m. This norm of gamma m, by the rules of norms, is the norm of this thing here, right? And by the rules of norms, a constant pops out in this way. It pops out as the absolute value of that constant multiplicative factor. So this is where we are using the rule of how norms are defined. So without specifying the norm precisely, it still doesn't matter, because we know that the norm of this object here is going to equal this because it is a norm. So this goes back to the properties of a norm. And we know that the norm of psi m, we know that that norm is always less than the sum of its components, the absolute value of its components divided by m. So if I know that, I can replace this, because this is a real number here, I can replace this real number, by this ratio, right? Because I know that that real number is always less than this ratio by assumption. So I do that replacement, and then the denominator here cancels with the numerator there, leaving only 1 over m, and that's what leaves us with this expression. And I guess also something else I probably should write down is if we look up here at this expression, we can substitute the expansion of psi m, which is, let's see, where did I define psi m? The expansion of psi m, right here, right? So alpha 1, phi 1, all the way to alpha n, phi n. And if I do that, I get alpha 1 m over this sum, alpha 1 m plus dot dot dot, and that's phi 1 plus, and then the same thing, dot dot dot, and then I guess it would be alpha capital N, which is the dimensionality of the space, and then the denominator is the same for all of them, and this would be phi n. So this is the basis expansion of gamma m, right? That's the basis expansion. This here is now the basis expansion of gamma n, because we know the basis expansion of psi m by our definition. The only difference in this definition here is we've kind of added an m to everything to label each of the psi m's that must exist by assumption. And as a reminder, those psi m's are such that by assumption the magnitude of psi m is always less than this expression. Okay. One of the annoying things about learning analysis is when you get into proofs like this, you constantly add names to things, you establish relationships in the beginning that are hard to remember through the end, and you create objects and then you create other objects that are a little more convenient, right? I mean, in principle, we didn't have to do this. We could have kept psi m throughout the whole thing and not introduced a gamma and just carried around all the coefficients, but that becomes a mess. And so then we create expansions of things where these terms get more complicated, and ultimately, this should be a little m here, right? And then what we're going to do again is the same thing. We're going to say, okay, here's our gamma m, which I just demonstrated the coefficients, but we're going to take these coefficients and we're going to rename them. We're going to call them beta. So this whole thing here is just beta 1m, and this whole thing here is beta nm. And capital N is the dimensionality of the space, right? The dimensionality of V. So we've lost, are we forgetting that from the beginning of the proof? I always had a lot of trouble. I always go back and forth in these proofs, and you'll hear me talk through going back and forth in these proofs a lot. So we've renamed these things. Now what's interesting about this is that, first of all, if you look at the way these are structured, these coefficients are structured, since the sum of the moduli is in the denominator and only one of the moduli is in the numerator, we definitely know that for each of these beta m's, the absolute value of those guys has got to be less than 1. So that's important. And it's also true that the sum of all of the moduli of the beta m i's is actually going to equal 1. And that's not too hard to see. If I take the modulus of this, right, if I take this and all the way and all the terms in between, what effectively happens is you end up getting the modulus of that up there, right? The denominators are all the same, so if I add them all up, just the numerator and the denominator are going to be equal, and you just get 1. But notice the series we're talking about now. The I here is just the sum over the expansion coefficients of the decomposition in terms of the basis. That's what this lower index of these things are. This upper index, m, is identifying what particular value of h we're playing with. As m goes up, that value of h goes down. And so, but each value of h has its own index m, and that's the index that is identified here, because that index m identifies the vector in the space psi we assume to exist that satisfies this inequality, and then we created gamma sub m from that, and then ultimately we've created this sequence of betas from that. So in a sense we have a new sequence. We have a sequence, I'll put it in red, beta I m. The sequence is a sequence in m, because m can go from 1 to infinity, right? It's an index that goes from 1 to infinity. So the sequence index is actually m, and there exists one sequence for each of the components, right? So each of these components can be understood to be a sequence in m. And that sequence is what I mean by this when I put it in the braces. So what I've really got is I've got n, capital N, the dimensionality of the space. I've got n sequences, and the sequences are indexed by little m. And those sequences are these sequences of coefficients of gamma. And gamma was something that was modified from our assumed vector psi. Now is where things in this proof get really clever and a little bit technical, I suppose. Each of these sequences is bounded. In particular, it is bounded by 1, the value 1. We know each of these sequences is bounded. So there's a really important theorem from real analysis called the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem, and actually W-I-E, hold on. I'm pretty sure that's wrong. It's W-E-I-E-R, and it's not Strauss with a U, it's with an A, right? I think that's right. Anyway, we'll never speak of it again. Every bounded sequence has a convergent subsequence. This is actually really an interesting theorem. Any student who's ever taken real analysis learns it very, very quickly. So it's a very elementary result. So this isn't like Zorn's lemma where you really don't play with it much unless you're a specialist. The Bolzano-Weierstrass theorem is actually Weierstrass theorem is actually very, very commonly used, and it's an immediately easy early result. But basically the idea is this: if I have a bound, if I have two bounds that constrain some infinite sequence, and I have it doesn't even have to be infinite, but I have a sequence here of points, and it doesn't really matter how the sequence is organized, right? The sequence can go, I guess each of these points would be called, say, xn, right? The value of xn and how they move between these bounds, between different values of n, really doesn't even matter. In fact, that's sort of the point of the theorem. As long as this is, let's consider just an infinite sequence for now, right? If this is an infinite sequence, and it goes on forever and ever and ever, then basically what it's saying is there's got to be some point somewhere in this mess, someplace, let's say it's here, that all of these points sort of cluster around, because we've got to fit an infinite number of points in here. And there's no way of fitting an infinite number of points in a bounded sequence where they're all separated by a small distance from each other. They have to accumulate. In fact, there's a place called an accumulation point. Somewhere they have to have an accumulation. Now, if that's the case, then we should be able to pick out points of this sequence, not necessarily going from n equals 1, 2, 3, 4, 5. I would write down 1, 2, 3, 4, 5, 6, 7, 8, right? Let me just do some more, because I'm going to need some more. 11, 12, 13, right? So we can imagine that xn equals 1 is here. Xn equals 2 is here. Xn equals 3 is here. Xn equals 4 is here, xn equals 5 is here, xn equals 6 is there, right? And what we're seeing is that this is the convergent subsequence, right? x1 is our first element of the convergent subsequence. I guess I called x3 was the second, and then I think I said x5 was the third, and maybe x9 is the fourth, and maybe x13 is the fifth. The point is that no matter where the points lie, in what order the points drop, I can always, in principle, pick out just the values of n that actually converge onto the accumulation point. The Bolzano-Weierstrass theorem guarantees that such a convergent subsequence exists. And if I pulled out just that subsequence, 1, 3, 5, 9, well, the subsequence itself, I guess, is actually x1, x3, x5, x9, x13, right? That sequence will actually converge directly to some accumulation point. So the theorem guarantees that there is an accumulation point. And the definition of a convergent subsequence is what I just said. It's you pick out from your arbitrary sequence xn, you just pick out the values that actually converge to the accumulation point. And the Bolzano-Weierstrass theorem guarantees that this can always be done. It's actually, I've done it for the real line here, but it's actually true for Rn. It's true for n-dimensional space. So the notational complexity is this. I write down xn as the original sequence, this bounded sequence. But now if I want to identify the convergent subsequence, which I know exists, I can now refer to x. And I guess what you would do is you would say Lj, right? Where Lj, j is just some natural number, and that's the index of the sequence itself. But Lj is the value of n that actually is part of this convergent sequence. So this number here would be Lj, or would be L of 1, 3 would be L of 2, 5 would be L of 3, 9 would be L of 4, 13 would be L of 5, forever and ever and ever. Because it's an infinite sequence, it must go on forever. And the convergent subsequence must go on forever as well. So we introduce this sort of counting function that just picks out those elements of the sequence that are part of the convergent subsequence. So that's the kind of notation we're going to be using here. All right, so now we have these convergent sequences. Well, we have these bounded sequences. It's bounded, look, right here, right? That's the definition of being bounded. Each element of this is less than 1 and greater than -1. So it's bounded just in the literal sense. And it's a real number, so it's bounded exactly the way we've depicted it here. By the way, all of these dots are supposed to be on the real line. I just got a little crazy with it and made them above and below the real line. But everything here is, the idea is that it's R, where n equals 1 here, R just the real line. Because remember, this is a real vector space. So even though it's n-dimensional, n-dimensionality refers to the number of components, not the nature of the component field. The field is the real numbers. Okay, so we have n of these sequences that they're sequences in M, and we have n different sequences. So now I've got another notational thing going on where I'm going to call those, I'm going to index them all together, and I'm going to write beta m k, where I identify the sequence by k. This identifies the sequence. And k goes from 1 to n, right? So there's n of these. But each one of them is a sequence, and the index of the sequence is m. All right, so to kind of review again, vector space V, we established that there was a sequence of vectors that are identified by m such that this is the case, and actually I should write this is 1 over m, right? And this is the assumption that is contrary to the lemma we're trying to prove. Obviously, we're looking for a contradiction ultimately. And from this sequence, we invented this sequence, which we defined its coefficients by beta through this prescription right here, right? That's how we define the betas. And for each member of this sequence, we created another sequence of vectors. This is a vector sequence. This is a vector sequence. And this vector sequence gives rise to n different component sequences. And each of those component sequences are listed here, and we talk about any given one by indexing the component itself with the letter k, and the sequence goes from m equals 1 to infinity here. And we know that this sequence, this guy, every one of those is bounded, right? And we know that the sum of all of them equals 1 by construction, by the way they were constructed. I should say, notice that when I say the sum of these guys equals 1, notice that this is true for any particular value of m, right? So this doesn't involve any limit on m. We're just summing through the dimensionality, so we're summing each of the components. But regardless, you calculate b using this formula for any value, for any m, meaning the derived from a gamma that's derived from a psi that satisfies that our basic inequality, that this basic inequality. You stop that process at any point, and they still sum to 1. That's a really important point. All right, so now we're going to focus on this guy here, beta 1m. And what we'll do is we're going to consider that as a sequence. So we're going to consider the sequence beta 1m from m equals 1 to infinity. So we're going to look at this sequence and we're going to say, okay, it's bounded, right? So because it's bounded, there is a subsequence that converges. So we will take that converging subsequence and call it Lm. So Lm is the index on that of just picking out the m's that actually converge. So this now gives us a new subsequence, BLM, and that subsequence converges, and we call the thing it converges to B1 hat. So this LM is exactly this function that we talked about before down here, where we're now just picking out only the elements of the sequence beta superscript m that actually converge. And so for each, so as m counts, as m counts, then LM is going to pick out just the convergent subsequence. It's kind of strange though, because m is actually this number here, and we're just using it as a regular index, as a regular just natural number index here. It might have been smarter to rename this guy k and make it k from 1 to infinity and then put k here. I don't know. I don't think so. It doesn't really matter. The point is that we do from it derive a subsequence in m, and that subsequence has a limit by the Bolzano-Weierstrass theorem again, because it's bounded, and we are going to now create that object, and this guy is the subsequence that is guaranteed to converge. And from that, we create a new vector. We create a new vector which we will call omega, and I'll call it omega LM, just to indicate that it's dependent on this subsequence of the first component's convergence, and that will be beta 1 LM phi 1. But we're going to take this sequence, we're going to take this subsequence indexing and commit every vector to it, right? LM phi 2 plus dot 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 beta n LM phi n. So every vector gets stuck with, every one of the vector components gets stuck with the same collection of indices that drove this one, the first one, into convergence. And notice, these guys are totally different sequences. They are also bounded, and they also have convergent subsequences, but those convergent subsequences have nothing to do with this particular convergent subsequence. Only the first one will be guaranteed to converge based on pulling that, well, that's how it was defined. It was picked. So the first one would converge. But these other ones, we're just now picking out essentially random elements of their sequence that have no particular requirement to converge whatsoever. So if m marches to infinity, then what would ultimately happen is this first one would march to its convergent number, whatever that number is, but the other ones would just randomly just flail about without any particular rhyme or reason. But here's what's interesting. Now think about beta 2. Beta 2 LM, it's still an infinite sequence, and it's still bounded. So this sequence has a convergent subsequence. And we would call that P of L of M. And now what we do is we force P of L of M upon this guy. And what do we end up with? We end up with omega L, well, I guess omega P of L of M. And that's beta 1 P of L of M, phi 1 plus beta 2 P of L of M plus ... Now what happens? Well, this guy is defined to be the convergent subsequence of this infinite sequence that forces beta 2 to converge. Right? I'm sorry. This guy is defined as the set of indices that defines the convergent subsequence of this infinite sequence here that causes beta 2 to converge. Now that is only chosen from the elements that already made beta 1 converge. So it's a subsequence of the beta 1 subsequence, but any subsequence of a convergent subsequence also converges. Therefore, this term still converges to beta 1, but now this term converges to beta 2. And so as m goes to infinity. And obviously you can repeat this process for each of the terms here. Each of the terms that are in the decomposition, the basis. And here's where the finiteness matters. This process has to terminate, right? If this process doesn't terminate, you can't get each of these guys to converge. So ultimately, you'll get PLM, and then you'll get, let's see, what would you get? You'd get P, you get R of P of L of M. And then you get S of R of P of L of M, right? And then ultimately, finally, it's done. So we call this last sequence, we're going to call it S M's, F sub n, just to get rid of all of these indices. So it'll be beta 1 S of M, phi 1 plus beta 2 S of M, phi 2 plus beta 3 S M phi 3 plus ... beta n S sub M phi n, right? And so this is now a sequence where these terms here represent counts that will, or represent sequence indices that go back all the way into each of the original sequences, right, where m equaled 1 to infinity. But so this is the original sequence, but we're only picking out values that lie in Sm, which is a set of numbers that could be, 10, 50, 222, whatever they are, but these are numbers that guarantee that each and every one of the components will converge, right? And so this sequence is the one that's obtained after we execute this process for each of the vectors of each of the components of each basis vector. So obviously, as j goes to infinity, as m goes to infinity, this is where that sequence ultimately converges. And notice that this sequence is a subsequence of this is a vector sequence, right? Because this side here, that's a vector, right? So this is a vector sequence, and that vector sequence is a subsequence of gamma m, right? The gamma m sequence. Now consider this sum. The sum of the components that are selected by our special final sequence as m goes to infinity, because these are all infinite subsequences, as m goes to infinity, the limit of this sum is going to equal the sum of the limits. And that, combined with the fact that a limit is unique, we know that this sum is always equal to 1, and so this sum is always equal to 1. So now the very end of the proof for this lemma is that, okay, so these guys got to sum to 1. That means at least one of these components here is non-zero, at least one, which means that this vector here always has a non-zero component. But we know that this vector is a subsequence of the gamma vectors, right? And we know that the gamma vectors, and it's an infinite subsequence. Well, this vector is an element of that. It's the limit of that subsequence. But we know that these gamma vectors were constructed so that this was true, that the norm of the gamma vectors was always less than 1 over m. But the problem is that this guy is going to 0 as m goes to infinity, the norm of gamma m, but its associated omega has a finite, a finite component as m goes to infinity by this expression. But one of the rules of a norm is the norm of a vector a equals 0 if and only if a equals 0. So this never can become 0. And therefore, it can never really be part of, connected to this gamma, whose norm limits to 0. So because of that, we now know that our original stipulation way back in the beginning, this, right, being true for all m, is incorrect, is wrong. And that means that when we asserted that, we assume that that vector exists for all h greater than 0, it's false. And if that's false, the only other thing that can be true is the lemma itself. Okay, so we've proven this lemma. All right, so now we'll just quickly use this result, that's all the hard work, to show that finite-dimensional vector spaces are complete, which is the same thing as saying that all Cauchy sequences in a vector space V converge in V for finite-dimensional vector spaces. So we're going to now take a sequence of vectors in our vector space, psi sub m, and we're going to say that's a Cauchy sequence, which means that psi sub m plus 1 minus psi sub m, right, that limit goes to, not to infinity, the opposite, goes to 0 as m gets large. So this is a totally different notation from our previous proof. We're going to assume our previous result, but now I've created psi sub m as a Cauchy sequence. But I will expand it the same way as before. Since it's still a sequence, we'll use the same notation where alpha has the little m in the superscript that ties it to the particular element of this Cauchy sequence. I could also express this idea as psi sub A minus psi sub V, as long as A and B are bigger, there's a certain big number M, well, I've used M somewhere earlier in this proof, didn't I? There's a big number out there, call it Q, that if A and B are both bigger than Q, then psi A and psi B are going to be less than some arbitrary number epsilon, arbitrarily small. So what we're going to do is we're going to write this Cauchy nature in this form, but our arbitrarily small number is actually going to be h times epsilon. With epsilon delta proofs, there's always a phase in the proof where they stipulate some inequality, not always, but often. And the right-hand side is some number that you have a lot of control over, but the way it's written seems oddly well chosen. Sometimes you'll see like epsilon over 4, right, or epsilon, and or 3 epsilon, or some weird number here. And it's because they know how the proof is going to end, so they simplify things in the beginning, and that's exactly what we're doing here. This right-hand side just has to be an arbitrary positive number. We can choose epsilon freely. H, however, is going to be the number that we stipulated in the previous proof, and that's sort of dependent on the vector space. But epsilon can be arbitrarily small. All right, so once we establish this, we can rewrite this expression, and we do it just by expanding this guy, right? Where A is some far distant spot in the sequence where this stipulation is going to be true. So we expand it just using this expansion right here, and we substitute that expansion right there, and we substitute that expansion right here. And in this case, m equals b. In this case, m equals a. And we're taking the difference in the two vectors, which is the same as this difference right here, and it's still less than some arbitrarily small number, which we control because we control epsilon. And the fact that, like I said, the fact that we have that h there is for later convenience. If we left the h out, by the way, right, this would still work. And try to follow along, imagining that the h was gone, and maybe I'll show you where, if I remember, I'll show you where it comes back in. So there's an epsilon here. So the next step is just to simply collect the terms associated with the basis vector. So this alpha 1a minus alpha 1b shows up as a combined term in front of the basis vector phi 1. So that's just a rearrangement of the terms here. But now we have one vector, one clean vector inside with terms, with component terms that are these differences of the components of these two vectors that we started with. And here's our spot, right? This is the big trick. If we look at this, this is just a vector. And we know that the norm, we have a norm of a vector. And we know that the norm of a vector is, and the vector is expressed here in this component form. We know from our previous work that this guy is always going to satisfy that inequality we just proved. That is, this norm will always be greater than h times the sum of the absolute values of the components. We've just proven that. There's always some number h for which this inequality is true. We chose that h right here, and well, that h is right there. So if this is always greater than this, but this is always less than this, I can divide through this inequality by h, and we end up with, well, this h, well, let's see, we end up with, well, put the h there, this has got to be, let's see, this has to be less than h epsilon, right? If this is less than this, but this is less than this, then this must be less than that. So let's just write that up right there. Now we can cancel the h's really easily, right? And now we get that, ultimately, we get the sum of the magnitudes, right, is less than epsilon. And that obviously implies that the sum of each of these, or each of these individually, are less than epsilon, which means that as I pick A and B to get bigger and bigger and bigger, no matter what epsilon I choose, this is always true. As long as epsilon is greater than 0, this is going to be true, and therefore this difference converges, right, or converges to 0 specifically. The difference between the components converge to 0. And that's important because that means that each sequence of the components, A, that sequence is Cauchy, right? And it's Cauchy not necessarily because our original sequence was Cauchy. It's Cauchy because we've shown the components are Cauchy, because this is the definition of Cauchy. Therefore, these guys are Cauchy, and we know that all Cauchy sequences, well, it's Cauchy of real numbers. All Cauchy sequences in real numbers converge because we know that the real numbers are complete. That's sort of a property of real number analysis. So therefore, we know that these sequences, these components all converge, and they were derived from the stipulation that this sequence here was Cauchy. Therefore, this sequence converges to a vector sequence whose components all converge, and it converges to real numbers which are in V, because V is a real vector space, so it contains any linear combination of real number components. So we've shown that's how you show that this is complete, that these components are Cauchy sequences. All right, so we've shown that all finite dimensional vector spaces are complete. Actually, let me try to restate that one more time. What I've shown is that the components of any Cauchy sequence, are themselves Cauchy sequences, which converge to real numbers in R. Therefore, any Cauchy sequence, as defined through the norm inside our vector space, every Cauchy sequence, the components of that Cauchy sequence converging to real numbers, therefore converges to a regular old vector, just a real number times a basis. So therefore the vector that this Cauchy sequence converges to is actually in V itself. And that's the whole point. The finite dimensional vector spaces are complete in this sense that all Cauchy sequences, these guys, actually have converge to a vector inside the space. Oh, and lastly, I promised I would comment that imagine if we had left this H off, right? Imagine if we had omitted that H there. What would have happened? This would have been just an epsilon, right? This would have been just an epsilon. We would have had our, we would have had our H here, right? And then I would have calculated that, then I would have made a division at the end, right? And I would have had epsilon over H over here. But again, I just rescale epsilon, and I rescale epsilon to say nu, where nu equals epsilon times H. Remember, H is just some constant, and then I replace everything, and it all works out exactly the same way. So just because we know how it ends, we start with the H up here. Okay, well that's enough for today. And now we're going to go on with more and more proofs like this to really get a feeling for how these spaces work. We're trying to get to the idea of Banach spaces, which are complete normed vector spaces, but can also be infinite dimensional. So we're going to start heading in that direction.